Good morning. I am Dr. Prathiba, Assistant Professor in Department of Mathematics. Today's topic is modern algebra. Let us see what are the basic concepts in modern algebra. Algebra classification, then some concepts in group theory. Examples of group theory are the content of this lecture. Before going to classification of algebra, let us see what is algebra. Algebra is a branch of mathematics that deals with constant, variables and arithmetic operators. Also, it is the study of algebraic structures. Algebra can be classified into three components. One is elementary algebra, linear algebra, modern or abstract algebra. Elementary algebra is a basic arithmetics, what we studied in our lower classes like addition, subtraction, division, multiplications, they are comes under elementary algebra. Then another one is linear algebra. The three components in linear algebras are matrices, linear transformations, vector spaces. And the most important topic in algebra is modern algebra or abstract algebra. Here also we can classify modern algebra into three components. One is a group theory, rings and field. Now coming to modern algebra. The basic algebraic structure in modern algebra is a group. For a group, let us consider a non-empty set G along with a binary operator star. Then the structure G comma star is said to be a group if it satisfies the following axioms. That is a closure, associative, identity, inverse. Closure is nothing but take any two elements A and B in G, then A star B is also an element in G, then star is a closure. Then for associative, A, B, C are three elements in G, then A star, B star C, that is equal to A star B star C. Then we call it as star satisfies the associative property. There exists an element E in G such that A star E equal to E star A, that is equal to A, then E is called the identity element. Then for each element in A, there exists one B such that A star B equal to B star A, that is equal to identity. Then B is called the inverse of A. If any binary operator which satisfies closure, associative, identity, inverse, we call it as a group. Suppose the binary operator satisfies only the two property closure and associative, we call it as a semigroup. If it have a identity element, then we call it as a monoid. Along with the inverse element, we call it as a group. Any group with a commutative property, we call it as a abelian group. The commutative property is nothing but A star B equal to B star A. Therefore, group is a non-empty set along with the binary operator star. Then it satisfies closure, associative, identity and inverse. Then we call it as a G comma star is a group. Examples for a abelian group and group are integer with addition, then rational number with addition, real number, complex number along with addition, then Zn with addition. They form a group as well as abelian group. Then order of element of a group. Number of elements in a finite set is said to be a order of a group. It is denoted by order of G. For example, A is a set which contains one element. Suppose A is a group, then order of this group is equal to 1. That is it contains only one element. Therefore, order of G equal to 1. Suppose B is another set which contains only two elements 1 comma minus 1. Then order of this B is equal to 2. Another important group is a permutation group or symmetric group. Generally, it is denoted by Sn. Symmetric group is nothing but the bijection mapping from a group to itself. Then the order of a symmetric group is nothing but A power m equal to identity. For example, A power 3 equal to the identity, then 3 is the order of a permutation group. Example, S3 is a symmetric group. The nature of S3 is A equal to 1 goes to 2, 2 goes to 3, 3 goes to 1. There is a cycle between the elements. Here the cycle of length is 3. This cycle is nothing but every permutation of a finite set, they form a cycle. Here the cycle of length is 3, therefore we call it as a 3 cycle group. Similarly, another example is S4. S4 is also a symmetric group which contains elements of the form 1 to 2, 2 to 1, then 3 goes to 4, 4 goes to 3. Here there is a 2 cycle is there. One is 1 to 2, another one is 3 to 4. Each cycle is with length 2. If the cycle of length 2 is, if the cycle with contains the length 2, then we call it as a transposition. The next one is a next one is a number of elements in a permutation group. Suppose the permutation which contains only 3 elements, then the number of element is 3 factorial. That means 3 factorial is 6 elements. Example S2, it is a n is equal to 2, therefore the number of elements in S2 is 2 factorial. The first one is identity element, that is 1 goes to 1, 2 goes to 2, another one is element in S2, that is 1 to 2, 2 to 1. Similarly, another example is S3. S3 means n is equal to 3, therefore 3 factorial, therefore number of elements in S3 is 6. Okay, these are the nature of 6 elements, that is one is identity element, remaining are the elements in S3. Next one is the odd and even permutation. Odd permutation is nothing but product of odd number of 2 cycles. If the product of even number of 2 cycles, we call it as a even permutation. Even permutation is called the alternating set. It is denoted by an. Number of elements in the even permutation is n factorial by 2. Suppose in a permutation group there are 6 elements, then the elements in a even permutation or alternating set is only 6 by 2, that is 3 elements. Another important group is groups of matrices. Groups of matrices are denoted by GL, that is general linear group. The set of all invertible n by n matrices under multiplication they form a group. The examples for a group of matrices is GL n comma z, n is the order of a matrix, then GL n comma q, that is the rational numbers also form a group of matrices, then GL n comma r, GL n comma c. If the matrix determinant is 1, then we call it as a special linear group. Example or general form of a special linear group is A, B, C, D, and A, B, C, D all elements belongs to the real number, and AD minus BC equal to 1. That is the determinant of this matrix is 1, then this group of matrices is called a special linear group. Another important group is a dihedral group. Generally it is denoted by Dn. Then elements in a dihedral group is 2n. Suppose n is equal to 4, there are 8 elements in Dn. Let us see the examples are the position of elements in D4. D4 contains 8 elements. For example, we consider one square. The 4 corners are colored with different colors. One is a pink, white, green, blue. The first one is a rotation of 0 degree. 0 degree means there is no change in their position. P goes to the same position P, W goes to W, G goes to G, and B goes to B. Another one is a rotation of 90 degree. That means the element goes to the next position, just it rotates on single rotation. That is P goes to the place of B, then W goes to B, then B goes to G. This is a rotation of 90 degree. The first one is identity element, and another one is a rotation of 90 degree, and the third one is a rotation of 180 degree. That means P moves to 2 places. That is P goes to the place of B, and W goes to the place of G, G goes to the place of W, and B goes to the place of P. Then the next one is rotation of 270 degree. 270 degree means it is a 3 rotation, 90 plus 90 plus 90. Okay, the fourth one is a rotation of 270 degree. Okay, these are the 4 elements in D4, but D4 contains 8 elements. The remaining 4 are, one is a flip about horizontal axis. That is, we keep the vertical axis as it is, then invert the elements along the horizontal, then we get a 5th element. That is, P goes to the place of G, W goes to the place of B, and G goes to the place of P, and B goes to the place of W. Another one is a flip about the vertical axis. Along the vertical, just we interchange the element, we get the 6th component. Then the next one is a flip about main diagonal. That means we keep the other diagonal as it is, just we change the main diagonal elements. The main diagonal elements G goes to the place of W and W goes to the place of G. Then the last one is a flip about the other diagonal. That means we have to keep the main diagonal as it is, just we convert the element in the other diagonal. That means P goes to the place of B and B goes to the place of P. These are the different elements are positioned in a dihedral group. Thank you. Thank you.